Simplifying radical expressions. So remember that a radical is a root. Okay, so before we get there, let's talk about prime numbers and composite numbers. A prime number is a whole number greater than 1 whose only factors are 1 and itself. So our prime numbers are 2, 3, 5. 6 is not prime because it's a composite number, which is a positive integer other than 1, which is not prime. 6 is 2 times 3. 7, 9 is not prime. The only even number that's going to be prime is the number 2. Then we have 11, 13, and so on. So if we have a radical, we are talking about something like this. The radical is the symbol. So this symbol is called the radical. We have an index, and we have something that's under this radical or under this root. It's called the radicand. So if we're going to remove terms from the radicand, we need the same number of terms all multiplied together as the index. Okay, so we're going to try to do this in terms of its prime factorization. You can do it other ways as well with the composite factors, but you have to be really careful that you go all the way down. So with the square root, the index is not written there, but we know that their index is 2 right there. Okay, so this is really the square root of 27, because 3 times 3 times 3 is 27. But if you break 27 down into its prime factors, 27 is 9 times 3, and then break it all the way down, and I'm going to circle the ones that are prime. And I rewrite 27 in terms of 3 times 3 times 3. That's what we've done here. This index is 2. Again, even though it's not written there, I know I need pairs. I need 2. So I can circle a pair of 3s, and it's going to come out as a single 3. And then this guy, this 3 that is all by itself, doesn't have a pair, stays under the root. Same thing here. If you have 3 times 3 times 5, this pair comes out as a 3, and the 5 is under the root. And we can even do this multiple times, right? If you have 3 times 3, and that pair comes out as a 3. 3 times 3, this pair comes out as a 3. These guys don't have pairs, so they stay under the root. Okay, so let's do some. And here's a note. You can do this with composite numbers as well. You could write square root of 12 in terms of factors where one of them is a perfect square. 4 is a perfect square. So what we're doing here is square root of 4 times square root of 3. Square root of 4 is 2. But you have to be really careful when you do this, and I'll show you in just a minute what I mean by that. Okay, so let's do some examples. I'm going to zoom in so I can have a little more room to write. Simplify each radical. So what I'm going to do is I'm going to rewrite every single radicand in terms of its prime factorization. Now I made a video already with all of these radicands already broken down into their prime factorization, and I went into a lot of detail on how to do that. So I'm just going to tell you what the prime factorization is. I'm going to show you one. There's often many ways to write one. And then if you need more help, you can revert back to that video. Okay, so 20. I'm going to ignore the root for now. I'm just looking at the radicand. 20. 2 times 10, and 10 can be broken down further. So 20 can be rewritten as 2 times 2 times 5, but 20 was under a root, so we put this under a root. Now we're going to circle pairs, and a pair comes out as a single 2. So square root of 2 times 2 is just 2. And the 5 doesn't have a pair. It stays under there. So again, we could write 20 as 4 times 5. If you take the square root of both pieces, this is the square root of 4 times the square root of 5, 2 root 5. You get the same answer. Let's try another one. 48. 48, there's actually lots of different ways to do this. We can rewrite the square root of 48 as the square root of 4 2s and a 3. And we're going to circle pairs. This pair of 2s comes out of the root as a single 2. This pair of 2s comes out of the root as a single 2. So we end up with 2 times 2, and then there's a 3 that we only had one of, right? So this is 4 root 3. So again, we could write 48 of 16 times 3. So we'd get square root of 16 times the square root of 3. You see we do get 4 root 3. But wait a minute, that's not the only factors of 48. If you did this as square root of 48 is the square root of 6 times 8, because 6 times 8 is 48, it's not obvious that you can pull out any factors. So that's why I'm saying we recommend you do the prime factorization. Because if you end up with something like 6 and 8, well, those aren't primes, they're composite. You'd have to break them down again. So it's just easier to break everything down all the way to its prime factorization. Let's try root 72. I'm going to write the prime factorization of 72. So the square root of 72 is equal to the square root of 2 times 2 times 2 times 3 times 3. I'm going to circle pairs. So a pair of 2s, that's going to come out as a 2. This pair of 3s is going to come out as a 3. So we end up with 2 times 3 square root of 2, or 6 root 2. And let's just take a moment and talk about why this works, just in case you're going, what? 2 times 2 is 4, right? So we have like 4 times 2 times 9. That's what I have if I combine the pairs. So we know that's the same as square root of 4 times square root of 2 times square root of 9. So 2 root 2 times a 3. And you can put the 2 and the 3 in the front and get 6. So that's what we're doing. That's why we're picking pairs. Okay, let's do some more. Prime factorization of 80. The factors themselves will always be the same, but you could have done, lots of different numbers to get 80. Instead of 8 and 10, you could have done 2 and 40 and started out with different composite numbers. But regardless, you're going to see that the square root of 80 will always be broken down into its prime factorization as 2 times 2 times 2 times 2 times 5. 1, 2, 3, 4 2s and a 5. Okay, now we circle pairs. Here's a pair of 2, that's going to come out as a single 2. Here's a pair of 2s, that's going to come out as a single 2. So we end up with 2 times 2, and there's a 5 that's still under that root. So 4 root 5. Okay, square root of 90. So let's do 90 in terms of its prime factorization. So we see that 90 is equal to 2 times 3 times 3 times 5. So the square root of 90 is equal to the square root of 2 times 3 times 3 times 5. I'm going to circle pairs. That's going to come out as a single 3. So we end up with a 3, and then we have a 2 under the root times a 5 still under the root. So 3 square roots of 10. That's how we write 90. Okay, and the square root of 100, you may know the answer to that. That's 10. That's one of our perfect squares, but let's pretend we don't know. So 100 we can break down into prime factorizations. Again, I could start with lots of different initial factors, but we see that 100 is 2 times 2 times 5 times 5. So if I take the root of 100 and I circle pairs, this pair comes out as a 2. This pair comes out as a 5. We get 10, as we thought. Okay, let's do some more. Prime factorization of 245. So the square root of 245 is equal to the square root of 5 times 7 times 7. Circle pairs. This pair of 7 comes out as a single 7. So we get 7 square roots of 5. 250, let's break that down into its prime factorization. So the square root of 250 is equal to the square root of 2 times 5 times 5 times 5. This pair of 5s comes out as a single 5. We get 5, and we have square root of 2 times 5. So 5 square roots of 10. Square root of 312. 312 can be broken down into a prime factorization. So the square root of 312 is the square root of 2 times 2 times 2 times 3 times 13. If I circle pairs, it comes out as a 2. And notice I just have another 2 to the first power, 3 to the first power, 13 to the first power. So this is 2 square roots of 2 times 3 times 13. I'm just going to multiply those. 2 times 3 is 6. So I have 6 times 13, which is 78. Okay. Let's do some more. Let's write 324 in terms of its prime factorization. So then the square root of 324 is equal to the square root of 2 times 2 times 3 times 3 times 3 times 3. We circle pairs. This pair of 2s comes out as a single 2. This pair of 3s comes out as a single 3. And this pair of 3s comes out as a 3. So we end up with 2 times 3 times 3. Wait a minute. There's nothing left under that root. So this must be a perfect square. So 18 squared is 324. Okay, let's try the square root of 380. So the square root of 380 is equal to the square root of 2 times 5 times 19. We circle pairs. This pair comes out as a single 2. So we get 2 square roots of 5 times 19, which is 2 square roots of 95. And let's look at the square root of 405. So the prime factorization of 405 is that. So the square root of 405 is equal to the square root of 3 times 3 times 3 times 3 times 5. And we circle pairs. That pair comes out as a single 3. This pair comes out as a single 3. So we end up with 3 times the square root of 5, or 9 square roots of 5.